We got lots of solutions here, and I guess maybe I'll go around the table and ask for people to say something that they think is interesting, perhaps, about their solution, or noteworthy, or something for discussion. And let me start on the other side, because I've been usually talking to the people near here. So, what about you? Did you, Kathy? Did you actually complete a solution to this one?
I was working with Neil and Karen,
Mm-hmm.
and Neil wrote a program which would generate and test possible values, and use that pruning technique we talked about at the end of the last class, using the suffix test. So I think that what we've done has been more or less discussed at the end of the last class.
Mm-hmm.
And so that's fairly straightforward. And then it pruned a lot of the possibilities and left you with a few conjectures, which then we proved by hand. Well, we didn't prove them all by hand. We gave a few example proofs. There were a few more than we wanted to prove.
Okay. Did you prove the hard one? No, the one about...
I proved the hard one, yeah.
The one...
I proved one with 1 star, 3 star, 4 star, 7. I showed that one.
1 star, 3 star, 4 star.
No, sorry, I have it wrong. I proved 1 star, 3 star, 6 star, 7.
Okay.
That's just an example of a negative proof. Okay, you have proof that doesn't work.
Oh, okay. Well, with at least one.
Yeah, with at least one. Yeah.
So you
sorry,
can write
one
star as 1 plus or 1.
Yeah.
Okay.
That's right. Okay. The other thing we came up with along the way was that we're working on an algorithm for doing long multiplication,
Mm-hmm.
and we found out that if you have something, for example, 1 6 star 7, which is an infinite family.
Mm-hmm.
Okay, it's interesting to notice that if you multiply that by 6, which is the repeated digit, then you get just multiply that by 6.
Right.
Okay, you get something with a lot of zeros in the middle. It ends in 2, and it has a lot of zeros in the middle.
Okay.
Okay.
40, and then a whole bunch of zeros like this?
Yeah, that's right. And I think it's first digits 1.
Like that?
Yeah.
Okay. Maybe we even put another 0 in here. I don't know.
Like that. Okay. Yeah, and it's interesting that all the cases for the infinite families that work, you have that property that you end up with the cross product having a lot of zeros in the middle. And if you think about that in terms of long multiplication, if you do sort of long multiplication, it means you're never adding n numbers. Okay. Okay, if you write out that in terms of just long multiplication, you've got 7
Long multiplication
times.
means what? This is in Australian terms.
Sorry. Okay. Long multiplication means you do multiplication the hard way. You write down. You multiply 1 6 star 7 by 7, and you write that down, and then you add 1 6 star 7 multiplied by 6, and so on. Might be easier if you use.
It's like longhand, but you do it with columns.
Basically, you're squaring it, not by.
I got
the idea.
Yeah.
Oh, okay. So I see. So the 6 is interesting because it's the thing that you're long multiplying by a lot.
A lot, yeah.
So, okay. So in other words, you have when you multiply by 7, you get something, but when you multiply by 6, you get 1 0 0 0 0 2, and then multiply by 6, you get this again and again and again and again. That's what you're saying.
Yeah.
So we just got a whole bunch of zeros in there.
Yeah, that's right.
Which is why this is working. That's another way to see it.
We didn't actually prove that was necessary. It seems to be a nice property you'd like to have, because it seems it would make things easier, but we didn't prove that it's necessary.
Yeah, I would be surprised if it could be. It seems that the probability is very small, but there's always a chance that it might, that some condition like this might occur. I thought of generalizing the problem slightly, so that we would ask for all pairs of numbers, so that if you write x and x squared below each other, and you look at these pairs of digits, like you have a 0 here presumably, and a 1 here maybe, and then some more zeros, and finally you end up with something over here like 7, 9, something like that. And you want these, instead of requiring that x be non-increasing, non-decreasing, that x squared be non-increasing, just require that these ordered pairs be non-decreasing. The same kind of a suffix condition can be used in order to generate these. So in other words, it says that whenever you have two repeated digits in x, then the digits below it in x squared would have to be in incorrect order. But otherwise, no condition. No, wait a minute. I was going to put x squared on top, and I was going to consider this to be my primary key and x to be the secondary key. That meant that x squared then would be in order. It would be assorted, but x wouldn't have to be. And I have the feeling that probably I would pick up all of the squares that are assorted that way, all the perfect squares. There'll be infinite families, more infinite families. In this case, it's a weaker condition. But there might be a few cases that I miss. And as I said the other day, that once you get, if you're trying to solve x squared equals ... and then you have some thing at the end here. 5, 5, 5, 8, 61, 8. I don't know what to put here. 41. It turns out that if you can, this will have a solution for x as long as you can get it started. If you can get it going far enough, then I can put any arbitrary numbers here. There's representation of pi or something like that, and I can keep on finding more and more digits of x, so that x squared would end with a given number of digits. And so you get every possible sorted pattern of digits in x squared is a possible square. As far as a live possibility that can't be pruned out, unless you have some kind of a technique for ruling out other cases. So by putting it in lexicographic order, by dictionary order, I mean, let's put x on the bottom instead. And these pairs are sorted 1, 0, less than or equal 1, 0. And so on, less than or equal. So whenever I have two digits equal in x squared, I require x to be different. The same kinds of methods that have been used for this problem could actually generate other families like this, but with a little. How would you know that you found all the squares that are increasing? That sort of requires that after you've got to a long, suppose I get a long ways, so I say that this, if I have a certain pattern here, let's make it an increasing pattern just for the heck of it. So suppose I have 3, 3, 3, whatever. And now I want to say, now is this going to work? If I stop at this point, well then I've got x figured out to this many digits, and the odds that if I square x and I look at the digits that come on here, that they're actually going to continue to be decreasing, very small. So I got very unlikely that it will finish. But I don't know of any theory that's going to help cut it off for the general case. That reminds me of something I did want to mention. That do you realize that if there's a solution to this in terms of x, that there are more than one, there are several solutions, because it turns out that does anybody have any idea how many if there's a solution at all to this equation, which means x squared mod 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 x squared. Suppose that there's an x that solves this Can you tell me how many other x's there are, mod 10 to the 9th, that would solve it?
Infinite number.
What?
There should be an infinite number. I mean,
The infinite number of x's? No, just mod 10 to the 9th. Just the remainder. So I'm only looking at numbers from 0 to 9 nines. Certainly minus x will also do it. 10 to the 9th minus x will be another solution. But there's always 8 or 0, provided that that this number here is not divisible by high powers of 2 and 5. Like 0, x squared congruent to 0, that has only one solution. And the reason is, somebody should be able to figure out why there's 8 solutions. See, I told you if you have one solution x, there's always another one you can get by taking the negative of. But there's another sort of obvious solution that's also going to work. Give the same square. I mean, it's only obvious if you've been playing with this first problem, but I thought it would be obvious. Maybe it's not obvious because I'm saying it too. I'm making you nervous, by the way. Mike?
X plus 5
Yeah.
is going to be 8.
Yeah, x plus 5 and 8 zeros squared will give you the same result too. And so minus x plus all those. So that's 4 of them. Now, there's the other ones I don't expect that to be so good, but it turns out that there's a number y squared mod, that y is definitely not 1, and y squared mod 10 to the 9th is equal to 1. There's of course 1 and minus 1, and 5 all zeros and a 1, and 4 all nines satisfied. But there's another sort of a fundamental solution to this one, and the reason is that it turns out that y mod 5 to the 9th is equal to 1, and y mod 2 to the 9th is equal to minus 1. Equal to 2 to the 9th minus 1. And so when you square it, it's 1 mod both 5 to the 9th and 2 to the 9th, and therefore mod 10 to the 9th, because they're relatively prime. So this funny number y, I had it written down once. You can just compute it to any number of places. Change 9 to infinity. Work with what they call ten-adic numbers, which is to say that we take numbers that have an infinite expansion to the left of the decimal point, and it just means that we approximate them by taking their remainders modulo powers of 10, and so there's some you consider the set of numbers that go on and on to the left, and we just define them by you can multiply such numbers, and you can even take square roots of such numbers, and if you can get started, and there's a square root of 1 that's neither 1 nor minus 1, and so xy and minus xy and xy plus 5,000 and minus xy plus 5,000 are the other 4 roots. So there's 8 roots altogether if there's a root at all. If this number y seems to have a pretty random decimal expansion. If its decimal expansion had some interesting properties, then we could probably get more squares, more solutions to this problem. But the general question then of find all x such that x squared is sorted. I see no way to resolve that problem. And someday, if you think of it, let me know. I got off on a tangent here. Kathy observes that when you do long multiplication, and if you you can notice this if you're programming this to do you have an array of digits and you multiply everything out in order to get the product and program the high precision arithmetic just the way we learned to do it in school. Then zeros seem to be occurring all the way here, and that's related to what seems to me that the reason we're getting these infinite solutions is just that 10 minus 1 happens to be a perfect square, or maybe it's more general. Maybe base 19 is also going to have solutions because 18 is divisible by a perfect square. I don't know, but somehow in our proofs, the fact that we had that 9 was a perfect square and 10 was just one more than a perfect square was leading to this thing. Maybe in your pumping lemma, did it suggest that you might get a similar phenomenon?
Well, just running the program that I had for bases other than 10 for turning up whole strings of, I think on base 5 you're getting 2's repeated all over the place. And
well, base 5, see 5 minus 1 is a perfect square.
But
That's
like
that one
base 9. Also
base 9, now that's the one.
Repeated. I think it's just anything that's a multiple of a...
that has a square factor? Okay, so the fact that the base minus 1 has a square factor is leading to that, and that would support this idea that that when we carry out the long multiplication, that we might be able to get a string of repeated digits, if not zeros. Okay. So in base 9 you were getting more. Okay, well I'll get to these other later. So let me see. Then Andy, you worked with who?
Well, I was working with Rich, John, Amy, and Marianne.
Okay.
We're kind of combination of groups. And I guess our strategy is very similar to Kathy's group. We just use that pruning technique of looking at the lower end digits, and we had the program come up with conjectures that digits could be repeated or not. And to prove those, well, I guess our philosophy is to minimize the effort, the human effort required by splitting up the work between machines and people. So rather than trying to write
That's why you have 4 people in the group. One machine and 4 people.
Anyway, so we basically just proved patterns by sticking an arbitrary string of digits x in front of whatever pattern we wanted, and then writing little programs to verify that, to prune off all possibilities of x by looking at the starting digits.
Okay. So, Andy?
Yeah, okay. I just did sort of the same thing, just tried to prune off possibilities. And
You and Arif work together now?
no, I was just working on my own.
Okay.
And and then the ones which the program couldn't prune off, I can improve in my hand. I still haven't done that completely yet. But.
Well, we'll have enough independent proofs, at least we'll believe them as we have this work. Right. So I want to get back to the subject of combined machine and handwork later. It's a good topic to talk some more about. Arif?
Our approach was similar, except that we tried to do the induction by we tried to write a program to do the induction.
Oh, okay. You and
Tang. What we had was we had some programs to do arithmetic on the strings, on the pattern strings, so that we could add pattern strings, or we could multiply them by a number, not by another string but by a number, and we could, given the square of one smaller string, generate the square of the string with something
Okay,
appended to its
so you
square.
have an algebra where you can say that this number times this pattern is equal to this pattern. Is that
Yeah.
what you mean?
Okay. And then we generated the conjectures we got the squares, generated the conjectures,
Mm-hmm.
fed in the conjectures about the squares,
Mhm.
said, okay, this is fine.
Mm-hmm.
And then again did the pruning.
Mm-hmm.
And
And I mean, the conjecture the result of a conjecture would either be yes, no, or maybe.
yes or no.
Yes or no.
That is for those which did not have two lengths of strings.
Okay. So you had a complete theory for that case, essentially.
Yeah, for the case with one string,
Mm-hmm.
one set of strings. For two strings,
Let me ask one more question. On your pattern, did you need to have a condition on the pattern that there were at least that n was greater than 0 or something like? I mean, did you have any conditions that you had to have it?
N meaning the length of
well, yeah, the number of repeated digits. Do you have to have
Yeah.
any lower bounds on those?
Yeah.
Okay.
We just assumed that the number was large enough.
Okay.
Can I ask you a question?
Sure.
We tried to do the same thing kind of with the symbolic multiplication. I mean, we tried to come up with an algebra to multiply a pattern by a pattern to get a pattern, etc. And we were able to multiply a pattern by a number, as you said. But didn't you find a place where you needed, in squaring the term, to multiply a pattern by a pattern, so that in some sense you got something that was variable in 2 dimensions? Like the term, when you're squaring 1, 6 to the n, 7, you can do 7 times 6 to the n quite readily, but 6 to the n times 6 to the n, you get kind of a square.
What we did was, we took the square of one lesser, if I want to find out the square of 6 raised to n plus 1, 7, I assume the square for 6 raised to n, 7. Okay?
You what?
I took as my inductive hypothesis.
Oh, you have an induction.
Yeah, I'm doing an induction, so I assume the solution for 6 raised to n 7, use that to get 6 raised to n plus 1 7.
So that's another kind. In other words, the induction is programmed, and the induction only needs, in order to verify that you get to the next step in the thing, it only needs a number by a pattern. Is that right? Now you said you were working with Karen?
No, Pang.
With Pang, okay. I'm sorry, I didn't hear this right, because I heard everybody was claiming to have worked with Karen. Okay, so that was like we were talking about on Tuesday. So on this, having an algebra with Q's and R's, the fact that you can multiply Qm times Qn, for example, gives some hope of having an algebra for certain classes of patterns, times patterns. But that's if you combine it. No, this is interesting. With induction, you didn't need that much power.
Well, it would work for double strings. Strings are 2 variable thing. I think it could be made to work, but we had made certain assumptions initially that the square of a pattern with 2 strings would contain only sums of. If it had one string of length m and another of length n.
Yeah.
In the square, we would only have strings of length m plus n. But it turned out there were some strings of length m minus n.
Yeah.
And programs are not designed to handle that.
Yeah. Well, it depended on m greater than n or n less than n. This is a similar kind of thing has happened when people write programs that are trying to automatically prove correctness of other loops. And they can usually do an induction. They can formulate a loop assertion or an induction hypothesis when there's one loop. But when there are 2 loops coming in, then they almost always break down.
No, but I have a feeling that it could be done. It's just that we have not written those programs.
Yeah, right. It could be done. Some program could do it. Yeah, but it raises the next the complexity probably is squared at least in that. Yeah. Okay, Dimitri?
I was working with John Woodfield, and our approach was basically the same. we did a suffix test for suffixes of length at most 10. So we found out, we guessed the correct patterns. We found out that the patterns that could not be discarded, the suffixes that could not be discarded, fall into 5 other patterns. We did with repeating 3s or 6s. We did some proof by hand for the squares of those patterns. We found, that is, we found the pattern of the square and expressed it in a way that the TA can guess, can be sure that it's correct. No carries.
Okay.
And then we fed in, for at least for those who had just one repeating string, one repeating digit, we fed in the computer the pattern for the number and the pattern for the square, and we proved that in general those won't lead to an acceptable number. And for the others that had 2 repeating digits, we did some work by hand. And the most interesting was, and there is the need for the second pumping lemma, the double pumping lemma.
Double pumping?
Yeah. And all 3s and a 5 and then all 6s and a 7, where you fail if the number of 3s is greater than the number of 6s. And
what was that? That was
3m,
yeah,
5, 6n, and a 7.
So this
If m is,
satisfies the suffix condition.
yes, when m is at less than or equal to n.
M is less than or equal to n.
But when m is greater than n, is n plus 1, then it fails.
It fails the suffix test.
Right.
Oh, wow. Okay. So this must have come up then in other people's programs, if their programs were correct, right? Okay. So in other words, this one keeps going and going and going until n steps, and then it cuts off. Wow. Okay. So then you have a complete rigorous proof that
yes, for base 10.
for base 10. Okay.
For base 16, we checked, we saw the patterns in base 16 that
Base 16.
the base 17.
17. Oh, okay.
There would be too many patterns to prove, and
I see.
our approach would fail.
But did you try any other bases besides 10 and 17?
We saw base 5 and base 6.
What happened in base 6?
In base 6 there were only, I don't remember.
2 or 3, I don't remember.
There was no pattern.
There's no pattern. You just had just 2 or 3 numbers. Okay. Well, that's 6 minus 1 is prime. It's sort of we've got to have a square in there if we're going to get something. Okay. Very interesting. So let me see if I covered.
I just have a question about that double pumping lemma part again.
Yeah.
How about if you consider, like to prove that one, consider 2, 3. Wait, if you're dealing with more 3s and 6s, then consider it to have the offset. I guess Roger called it B, the right hand offset to be 2, 3 to the n 7. Then when m gets large enough, you can use the pumping lemma. And if there are more 6s, then you consider it to be a left offset of however many 3 to the n 5.
Okay. So you're let me erase this and go back. I'm saying that we had the lemma, we had the theorem on Tuesday, and so you might consider this if m is large.
If m is great, you have 2 cases. If m is greater than n.
Okay, so suppose m is greater than n, then we consider this to be 3 to the m plus n or something plus b.
Yes.
Squared, where b is all these numbers to the right, and provided that we get m plus n large enough with respect to b, then that theorem tells us that this will work for all sufficiently large m or not. That's the point. So if m is large, you would get a failure from the other one if we had a sharp estimate for how large this has to be. And perhaps it doesn't have to be much larger. I mean, maybe m equals n plus 1 will be large enough. Yeah, good. That's a good point. And you're saying when m is less than or equal n, then you would consider this to be 6 to the
you make the
6 to the n, 6n plus 1, and then you have your, there was another term in here then, 10 to the n times, what do we call it, b or c? I forget, c. I don't remember how we did this. Okay, so then c would represent a small number of m's, and as long as that, the point is that the pumping lemma that we had on Tuesday said that if we take this repeating part and let it get large enough, then all those numbers are sorted or all those numbers are not sorted. And large enough depended on the size of the other constants in here. In this case, it would depended on b. In this case, it depended on c. And if we look very closely at exactly what it means to be large enough by chasing down our proof and seeing how much, it might be sharp enough to rule out this case, because c would be something that's the number of digits in c, and including the 3 and the 5, would be small enough with respect to n here. And similarly, the number of digits here would be small enough with respect to this m plus n. Okay. Now let's see, then left is Mike and Roger.
In addition to the stuff that Roger refined his pumping lemma a bit and wrote a program to test numbers using it.
Oh, I thought you were going to say you wrote a program to refine pumping lemma.
Wrong.
It should be pretty neat. Okay.
I had written a program.
Yeah.
I've written a program which sounds a lot like Arisu and Peng's.
Oh, yeah.
And basically had the same problems with it. It only worked if you had one repeating string in it. And so I've tried writing a program which handles more than one repeating string. And it looks like your hypothesis that the complexity gets squared is true.
That was only a conjectured lower bound.
Yeah.
I don't say upper bound. Yeah.
Like I said, it doesn't work yet.
But you do have something that proves induction. In other words, it formulates induction hypothesis and sometimes says yes or no.
The first program does
the first
that.
Yeah. Mm-hmm.
And essentially, it starts out the way the simple ones do, building a number up from the right-hand side, and as soon as it starts seeing repetitions, it then tries to form an induction hypothesis and prove it.
Mm-hmm. A repetition just does it have to occur twice, or just at 4 times? What?
I picked 4.
4. Oh, okay.
Good arbitrary number.
Well, I was wondering about whether or not this number of repetitions should be considered as part of a branching. In other words, you have a case of branching, and you can say, well, either n is greater than 2 or n is equal to 2. And if n is equal to 2, you have a case that you can try without considering that a pattern has occurred. But if n is greater than 2, then you can use a pattern that relies for its proof on the fact that n is greater than 2. I'm not sure if this is an important idea or valuable idea or not. But that is, instead of choosing an arbitrary number, consider that's just the one other thing in your branching in your tree. That is, you either go through a pattern or you don't, and something like that. And you have to catch that you don't get infinite. Yeah. Okay, so it's that's it's a program that you think might work soon, huh? Yeah. Okay. Roger?
Well, got the double pumping lemma.
What is the double pumping lemma?
Well, double pumping lemma.
Right on the other board here.
Not to get too specific about it, but well, just if you put it in terms of 3s and 6s.
Okay.
If you've got say 3 to the m, 6 to the n. Well, yeah, you got something added at the beginning, something added in the middle, and something added at the end.
To the
n plus n.
n plus this plus b. Is that what?
Well, b, and then there's also another thing you can add something times 10 to the n.
Oh,
in the middle.
Okay. b times 10 to the n also. Okay.
The idea is that if m and n are sufficiently big, and sufficiently big depends on b, d, and c, you can expand them simultaneously. You can get the same sequence of digits in the square.
Then all of these are good, or all of them are bad.
Yeah, essentially.
Well, and this, so the proof is somehow gets around the problem as to whether m is greater than n.
Well, it assumes that you just pick m is m minus n is fixed.
M minus n.
You just leave that fixed, and then you can. When you look at the square, you've just got.
You consider your proof says let k equal n minus n.
Well, actually, the proof had n plus nu in place of m, and then I just worked on n.
So this is.
But it's, and then you can do another one with n plus well. You do one proof with n plus nu in place of m up there.
Yeah.
And then you do another proof with, say, m plus mu in place of n.
Where mu and nu are non-negative.
Yeah, mu and nu are just non-negative and fixed.
Okay. And then combining those two. And Andy gives you what you Golding thinks that maybe you could get it as a corollary of the single.
Oh no, you can't.
Not quite good enough, not quite sharp enough.
I think the problem with trying to use the single one twice is that to apply the single one, you would have to have an infinite number of base cases proven. You have to prove have to have arbitrarily large base cases to start pumping, and you need the double one to get those.
Okay. Well, but
in the example with 3s and 6s and 7s, to pump the 3s you need more 3s than 6s, and so you have to prove it you have to prove at least one case for each possible value of 6 with more 3s without using the pumping lemma first.
Okay. Well, some discussions like that, and then we have a formal proof of impossibility, of deriving it as a corollary. It's a matter of, but it's.
Did this proof cover more than the case for which m minus n is fixed and they're increased in kind of lockstep?
No.
So that's all it covers.
That's all it covers. To actually close out all the possibilities on base 10, you've got to combine the single lemma with the double lemma very carefully.
So you combine that one with the two over there, and this one will generate all the base cases for that one.
Well, what you have to do is you have to start out with a large enough number of 6s so that up until a certain number of 3s, you'll be able to pump the 6s. Then once you get to the point where the 3s get too large to pump the 6s, then the double pumping lemma has to be able to take over, pump them both out. Okay. In the meantime, you keep adding. And then you can keep adding 3s on the end until you're able to pump the 3s, and then that.
it sounds like this ought to be, it's going to be very difficult to go through all the detail. But the main idea. But have I stated it correctly here?
Yeah, that is the basic.
There exists a function capital N of B, C, and D such that all of these are equivalent to each other as far all sorted or all not sorted. That's right. Now, and that's proved using some combination of techniques from this.
It's the same technique as with the single lemma.
So there's actually the added condition that m minus n is fixed.
Well, he's claiming that he's proved this in general, though, that there exists a function capital N.
You prove it for an arbitrary fixed difference between m and n.
So you have an infinite number of equivalent classes.
But then there's a single number capital N.
The classes are...
See, that's the thing is you don't. They have to grow in lockstep.
So I
mean, showing just one. That's why that's why you have to. You just want to write down a sequence of numbers, okay?
Sequence of numbers.
Just write down like 6 to the. Put down 6 to the 6, okay? Okay. Actually, okay. Put down. Well, you're going to do a lot of writing that way, but.
Oh, okay. Well, maybe you want to write it. I just wanted to try to. First of all, the question we have two. Anil is saying you've only proved a statement that seems weaker. You've proved two statements of the form. When n. If m minus n equals k, positive, negative, or 0, there exists an n sub k for which m greater than n sub k of BCD has this property. Now, the other theorem is there exists an n such that for all mn greater than or equal to capital N, we have they're all sorted or they're all unsorted. This is saying for all k, there exists an n sub k. Those are not obviously equivalent statements.
Actually, it's one of these things that's a lot easier to see graphically than you got a bunch of 6s. So let's assume that just for now that we have enough. Okay, and just fill this all in with 6s. Okay, and okay, so we consider 3, 3, 3, 3, 3, 3. Okay, at some point we get out far enough, say 4. 3s that the always the same number of 6s here, and then you get 3 out this much. Okay, like this. And the idea is, in order to use the double lemma, you need a minimum number of 6s and 3s. Okay, so you got some n where you have to have at least that many 3s and at least that many 6s. So say that point is reached here.
Okay.
And to use the single lemma to extend the 6s, you can't have any more than a certain number of 3s. And the problem is you've got to search out far enough so that there are enough 6s that these points overlap. That is, you have a set of 3s here that you can either just push out this way or double them. Okay, so like you can have 4 3s followed by any number of 6s, well, followed by this number of 6. Excuse me.
Reminds me of the number of the beast.
Let's see.
Let me start you back again. You first prove this, and then you show that establishes this. There's two possible theorems here. We have a weak form saying that for all k there exists an n sub k, so that whenever m and n go in lockstep, then we have that bound. And here's one that says that there exists an n independent of, depending only on b, c, and d.
Oh, well, okay, now this is the one here.
That's the one you proved.
Yeah, it's, it's not quite the form A. Yeah, this is definitely true.
Mm-hmm.
That's,
Thinking my feet.
Okay, well, let's just say that the second one, that it doesn't look like the triple pumping lemma is ready yet. For solution.
all I'm trying to show here is the idea is you have it search all of these, and it searches down far enough until it can just pump the single 3 out. Okay, and this will cover all of the different patterns of digits that can appear.
With 6 sixes,
With any arbitrarily large number of 6s and arbitrarily large numbers of 3s.
Mm-hmm.
Because then what happens is that given some 6 to the...
That's a no-no.
Oh, we're not supposed to write below this line. Like the chord doesn't exist.
Given some 6 to the k, 3 to the l, whatever, k is larger than that number. That would be large enough that you can pump it down, and you'll either hit a point where k gets to this number of 6s, and you'll still have a lot of 3s, in which case it'll fall in this area. So it'll be something you've covered.
So you are deriving it by means of the first.
You need both of them.
Okay. All right. So in other words, you have this weaker form, this form, and you have the one we had on Tuesday. Between the two of them, you exhaust all the cases of the squares. That's what you're saying.
There's a program, and it only works for base 10.
Okay. When you did have some other results, so if you found that, for example, in base 9, you had an example. Is it easy to quote it? Is it?
Well,
you have a note about it?
I think the one I printed out was base 5.
Now, base 9 is the one that I was most, because 9 minus 1 is not a perfect square. Okay, we don't have, if you did have it, that would be nice, but don't have one. Okay. So I think I've covered all the groups then, is that correct? Let's see if we can't use a few minutes to think of what, if anything, we've learned about while working on this problem, other than the fact that all the squares that are sorted, and x and x squared both are sorted, are a certain set. What do we find more generally? Well, we learned some things about numbers, about number theory that might have been new. I learned things about rep units that I didn't know about as far as minimum coins are concerned and things like that. But I'm trying to abstract away a little more from that. And I think one of the key things has been that we have to, is the issue that Andy brought up earlier about what about the interchange between programming and having a computer do everything automatically and doing something by hand. Now, it's possible to set ourselves a goal that we'd write a computer program that would solve all problems in the world, or we can find some cutoff and say, no, our program should solve as much as some reasonable amount, and after that, after all, we could, we're there, and we can be available to help write the program. Sometimes it's easier for us to write a proof than to write a program, and the program might even be wrong because I mean, a little less reliable than our proof if it gets too complicated. So one of the things that seems to come up here is that we try to find a subset of all mathematics, some small theory that we can actually that's sufficient to do the kind of problems that we're interested in. This seems to me very much like the idea of inductive closure when we're trying to just prove something by induction in a mathematics course, where you have a problem that you want to prove by induction, but the theorem that you want to prove isn't strong enough to prove itself by induction, so you need to prove something more, and then you can prove. Then it's easier to prove more because more will also carry through in the induction steps. So you look for something so that all the smaller cases of the general thing you're trying to do is also included in it. And it's rather similar to trying to search for what you need for a class of things that you could handle in a program like this. For example, we needed to be able to deal with multiplying a string of some pattern by another digit, and so it's natural then to search for theories, that says that if we have a pattern, we can if our computer is going to represent now not just numbers but patterns of numbers, then what operations do we have to be able to do on patterns in order to keep within a system that will be enough to carry out the whole proof. In order to do this, you start out usually it's like a closure process that you start out with the smallest amount that you have to do. You need numbers, you need simple patterns, and then you see, well, now let's see, what else do I need? And you come to the conclusion that, oh yes, I need to multiply a pattern by a number. So you put that in. Then Arif pointed out that he was able to get a lot of mileage out of just that because he could use induction without having to multiply pattern by pattern explicitly. On Tuesday, with the identities I was writing down, like Q m times Qn equals R m plus n minus Rm minus Rn. The point of that was to try to say that we could have a computer that was able to deal with linear combinations of Q's in the x variables and linear combinations of R's in the x squared variables, and then we could imagine a program that was able to manipulate a formula like R sub m plus n minus R sub m minus R sub n. So the program wouldn't have to manipulate all formulas in the world, but this kind of formula looked like we might need it in our theory. Several of you figured out how to do without that. Several of you figured out how to do it by hand with the computer telling you what the cases were to verify, and just then presenting you with a small set. I think this has given us a little bit of insight into interactive problem solving, letting people and computer work together. And I raise this because problem 2 is going to be a lot of that. Problem 2 will be the cryptanalysis problem. Has a lot of that. Now let's see. What was the answer about base 9?
There's 1 followed by 4s and 5.
So let's give me an example in base 9 that I can just write down.
Okay, 4, 4, 4, 5.
4, 4, 4, 5, base 9 squared is equal to?
It's 4 2s, 3 6s, and a 7.
Okay. So there's an example then where 9 minus 1 is not a perfect square, but it still has patterns like this, and presumably this generalizes then to any number of 4 or 5. Yeah, okay. And 4, 4, 4 is 1/2, isn't it? This is just a little more than 1/2. Base 9. When you got an odd base, you can't represent. I mean, it's something like 0.667 is 2/3. 0.445 is 1/2 in base 9. So we're squaring it and getting 1/4, sort of in base 9. Okay, well, any other comments on what general ideas we might have, insights we might have gotten from working on problem 1? So, it's hard really to say whether we learned anything. We had only a week and a half